In the last video, we introduced the kinematics variables. In this video, we will see some important relationships between them. Let's start by reviewing the three variables of kinematics. Displacement, that's delta x. That's the vector change in position. Velocity, that's v, the vector rate of change of position over time. And acceleration, that's a, the vector rate of change of velocity over time. In this course, we will examine situations where acceleration is constant. There are many such situations in both the natural and the engineered world. In these cases, the kinematics variables can be interrelated in different ways. I've always called these interrelationships Newton's toolbox equations, so that is how we will refer to them in this video and beyond. Say we have an object like a car that is accelerating. If you take two photos of it at two different points in time, you'll see it has physically moved and its velocity has changed. We can therefore talk about several quantities relevant to the car: its displacement, its initial and final velocities, its acceleration, and the time that elapsed between the photos. Let's look at some further relationships between these quantities. Let's start with acceleration. The definition of acceleration, I'm going to write it slightly differently, is like this. Acceleration is equal to final velocity minus initial velocity, all divided by time. This is the definition that we used in the 101 class. In the 103 class, the related definition looks something like this. Acceleration is equal to the derivative of velocity over time. These two equations are related to the same concept, but they are saying slightly different things. Strictly speaking, this is an equation for average velocity, and this is an equation for instantaneous velocity. Remember that for the purposes of Newton's toolbox equations, acceleration is constant, so instantaneous velocity and average velocity are one and the same thing. So we can derive Newton's first toolbox equation like this. I'm going to take the equation for average velocity and multiply both sides by t. There. This is Newton's first toolbox equation. If you prefer to use calculus, here's how we would do the derivation. I'm going to multiply both sides by dt. And then take the integral. Now, remember, acceleration is constant, so it can come out of the integral, and we'll end up with integrals that look like this. And now we can perform the integration. The integral of dv is the change in velocity, which is v final minus v initial, is equal to acceleration times the integral of dt will be the change in time, also known as the time elapsed. And so we end up in the same place. So this is Newton's first toolbox equation. And whether you're using calculus or not, this is what the equation says. If acceleration is constant, then final velocity minus initial velocity equals acceleration times time. Now, the second toolbox equation is going to dovetail from where the first one left off. If you're in my 103 class, you should see what this derivation looks like. It does involve a little bit of calculus, but let us see what we can do with it. The first thing that I'm going to do is I'm going to move this initial velocity over to the other side. So that's going to give me final velocity is equal to initial velocity plus acceleration times time. Now, suppose that I don't know how long the object has been accelerating for, and I wanted to find out what its displacement was. How do I go from its velocity to its displacement? Well, velocity is the derivative of displacement. So to get back to displacement, I have to integrate it with respect to time. But I can't do that to just one side, I have to do that to both sides. Integrating velocity with respect to time will give me displacement. The integral of vi, initial velocity, with respect to time gives me vi times t. And the integral of at with respect to time is going to give me 1/2 at squared. So this is the second toolbox equation. This equation says that the displacement of an object is equal to its initial velocity times however long we were examining it, plus 1/2 the acceleration times that time squared. The third toolbox equation is derived from one of the definitions that we saw earlier, the definition for average velocity. Remember that the definition of average velocity is displacement divided by time. But if the acceleration is constant, there's another way to figure out average velocity. It's like this. Average velocity can be treated as just the initial velocity plus the final velocity, all divided by 2. And this should make sense, because all we're doing is taking the average of the initial and the final velocities. So this is the third toolbox equation. The fourth toolbox equation is generated when we take the third toolbox equation and the first toolbox equation, isolate time in both of them, and then combine. So to do that, I will first isolate the time in this third toolbox equation. I'll multiply both sides by 2t. When I do that, this 2 and this 2 will cancel, and this t and this t will cancel. So that's going to give me t multiplied by v initial plus v final is equal to 2 times delta x. Now, let's now take the first toolbox equation and isolate the time over here. I can do that by dividing both sides by acceleration. Acceleration cancels out, and we have time is equal to final velocity minus initial velocity divided by acceleration. Now comes the fun part. We are going to take this expression for time and plug it in for this expression for time. Like that. When we do, we get the following. V final minus V initial divided by acceleration. All of this multiplied by v initial plus v final is equal to 2 times delta x. There are two things that I can do now. First, I can multiply both sides by acceleration. I'm going to stick this in here, which means that acceleration will cancel from the left side, and I'll have 2 times a times delta x on the right. Second, we now are left with v initial plus v final multiplied by v final minus v initial. This could also be written as v final plus v initial, like flipping around the order, multiplied by v final minus v initial. You might notice that this is a pattern that you've seen in your pre-calculus class, the product of a sum and a difference. So whenever we have that, we end up with v final minus v initial squared squared. These two binomials will multiply together to give us v final squared minus v initial squared, and all of that is equal to 2 times a times delta x. So this here is the fourth toolbox equation. These then are Newton's toolbox equations. They can be applied to any situation where acceleration is constant. If acceleration is not constant, these equations don't apply, and we would need calculus to find relationships between the various quantities. Remember, there are overall 5 variables that are involved in these equations. You'll notice that each of these equations contains 4 variables. No 2 of them share the exact same 4. They're all in different combinations, which means each one is used in a different context. Each one is used when different pieces of information are available. This video has introduced Newton's toolbox equations. In the next video, we will see examples of how to use them.